How do you know if your motor oil is doing its job? You test it. But how? I'm Gale Banks, and I'm in AMSOIL's Chem Lab to find out. It's time for Speed School. In the last episode, I got one serious chemistry lesson. Today, engineer Dan Peterson introduces me to Dale Beck, a lab chemist who will teach me how to test motor oil. It's day 3 of my lubrication education.
All right, Gale, we've had a lot of fun here so far.
So far, yes.
So
more to come.
Yeah, more. Oh, this is really fun here. So we actually talked about, components and materials that are used in a typical motor oil. So we got a pretty good baseline understanding of that. That's only a part of it, because when we formulate a motor oil, we got to prove that it works. And we're going to do a whole bunch of testing on it before it ever sees the inside of an engine.
Gotcha.
So what we're going to do next is we're going to go through our whole lab here, and we're going to talk about a number of different tests that we have.
Why don't we start with cold cranking?
Well, let's hit it. This is Dale Beck. He's a laboratory chemist.
Hi.
That's going to help us through some of the details of each one of these laboratory tests.
So this is cold crank testing?
This is our cold crank simulator. This is required for all motor oil lubricants and diesel oils. This is where you get your winter rating, the 5W, the 10W.
Yes.
And we did talk about that in detail and the importance of the W rating.
It's essentially a giant rig where it sucks the oil up, and it's got a little spindle so that it actually rotates this spindle inside, and it measures the resistance to rotation at specified temperatures. Using that torque value, it calculates the viscosity.
So the spindle drops into the sample?
It pulls the sample up into the unit.
Got it.
And inside, it's basically just got a pump that pulls the oil in, and it's just a little spindle inside of a cell.
So the torque?
And it's just measuring torque at specific temperatures. We have a chiller bath, and we can program it to run at temperatures in 5-degree increments. So like a 5W30 would run at -30 Celsius, and you can run a 10W at -25 Celsius.
And this refrigerates the sample?
Yes, yes, it pre-chills the sample before it runs it.
To -35?
Yes.
Oh my God. All right.
So that's how we get the winter rating for the 5W, and over here is how we get the 30 weight.
Let's have a look.
These are our viscosity baths. This one is run at 100 degrees Celsius or boiling water temperature. We have this one over here that runs at 40 degrees Celsius. This one over here at 100 degrees Celsius, this is where you get your 30 weights, your 20 weights, your 40 weights for all your motor oils and diesel oils.
So Dale, what are we actually measuring here? I see you got a couple red rings on there. What does that mean?
So these are viscometer tubes. So each tube has an oil sample in it, and there's 2 lines, an upper and a lower. So what we do is we pull oil up to the upper line, and we let gravity pull it down.
Kind of like an hourglass, right?
Like an hourglass, down to the lower line. And we just measure the amount of time it takes to get from the upper line to the lower line.
And that's converted into viscosity then?
Yep, we have a constant for each tube at each temperature.
So this is real basic foundational stuff for us. Measurement, again, of that actual thickness of the fluid at different temperatures, which we learned was really important for formulating motor oils.
And we're doing the same thing in this?
Yes, this one we're just running at 40 degrees Celsius. So all of your compressor fluids or your ISO VG, so an ISO 46 or an ISO 460, those are all based off of this bath and this temperature. So we run both. This is how we calculate our viscosity indexes for each of our products. And every raw material, every blend, every finished product is tested in these.
And temperature here again?
Is 100 degrees Celsius.
Got it.
Yeah. So over here we have our ICP, which stands for induced coupled plasma. So what we're actually doing is we're burning the oil at extremely high temperatures, not as a gas, but as a plasma. And what it allows us to do is as each molecule gets burned, it emits light. And this device, this half is actually the torch, it burns it. So inside you can see there's a torch. It burns it over 3,000 degrees Celsius. And on this side is the detector. So inside is a bunch of mirrors and reflectors and detectors that are measuring different wavelengths of light that each element in that oil gives off. So we can use this to find calcium, magnesium, iron, copper, aluminum. So we can look at our products.
Silica.
Silica, you can see that. We can see boron, molybdenum. We can even look for that in terms of friction modifiers.
So it's a spectrographic analysis.
Yes. It gives us kind of a fingerprint of each of our products. So we have a file of each single one that we could reference against if there's ever a question or doubt of whether or not it's our product. And then we can also use it for used oil analysis to determine
Yes.
wear metal increases for oil consumption or varnish testing. We work very closely with our mechanical lab. So we make a lot of oils for testing for them. They'll run it in their rigs. They'll give us samples back as it's running, and we'll actually test it and monitor the equipment. And we usually tell them when it fails and to kill the test.
Yes.
Here's a good example of where this is used. So a diesel engine's got a lot of iron in it, right?
Yes.
So we can actually take a look at small particles of wear metals that come off in that application, and we can actually chart and figure out a wear rate for that specific application. And if we put like a different lubricant in it, then we could actually change the rate of wear in that application.
Yes.
And this is the instrument that tells us about that.
Got it. There's millions of dollars of investment in this lab. I love it.
So we'll go over and check out our water tester. So now this is measuring water content in oils. So for a lot of our industrial applications, there's requirements on how much moisture content can be in the oil.
Yes.
We also use this for a lot of our raw material testing. Since we live in northern Minnesota, Wisconsin, we have some pretty harsh winters.
So you would pull a sample
Yes.
out of one of those tank cars
Yes, we would.
and come to here.
Yes, part of our quality control checks is to measure, first we do a crackle test, which is just seeing if there's any water present. And then if we do find
That
any,
sounds like heat.
it does sound like heat.
What do you just put it on a hot template?
Yes, we do. Yep, pretty much
Wait
water
for
in
it to crackle.
Yeah.
water in a frying pan.
Yes.
If we do find moisture, we can actually reject the whole rail car. Usually they like to know the exact concentration, so we'll come over to this instrument and we'll get an exact amount of water that we can report back to them.
So when you talk 30 parts per million, that's very low water content.
It is a very low.
And this will go there.
This will go there.
Wow. My God.
And water is really a tough contaminant to deal with for oils, especially for our motor oil. So anybody, your viewers have seen you pull the oil cap off and you look and there's kind of a mushy ring around there, emulsified ring. That's a high water content area with some oil vapor, and that emulsified stuff is not good if that was what your whole sump looked like. So water can do a lot of damage.
How does this thing work?
So it's actually really simple. We have this piece over here, which is just basically a hot oil bath, and we inject the sample into it. And all it does is it evaporates the moisture through the small tubing and into the reactor chamber,
All right.
which is basically just measuring the conductivity of that solution. So the more moisture that goes in, the more conductive it is.
Got it.
And it uses that electrical conductivity to measure the amount of water.
You could have a sensor like that in your oil pan. That would be cool. Whoa, what do we got here? Looks like a cappuccino machine.
No, this is actually our particle counter.
Oh, damn it. I wanted to.
I wish we could have some cappuccino. No, this is our particle counter. We're actually using a laser to look for particles in oil samples. A lot of our industrial products have particle count limitations on new oil. They don't want the oil dirty when it goes into the new application. It's actually looking at the shadow. It shines a light through and the detector looks at the shadows. It counts the number of shadows and the size of the shadows, and it reports that information for us.
In new product.
In new product.
Got it.
One thing that's interesting about this, you think about why are you caring about just a few particles, Gail, but in gear lube applications where you've got teeth that are gnashing together at really high pressures, if those particles get in there, they can actually create little pits, and then those little pits propagate, and then a crack forms between those, and then that's the start of actually cracking off a gear tooth. And it can start right here at a small amount of particles. That's why we filter things to a very, very low level of particles in the lab and then measure it, because we don't want to start with any particles in the system.
I appreciate that, but I really wish it were a cappuccino machine.
Me too.
So what have we got here, Dale?
So this is our NOAC volatility tester. What this is doing is we're taking a small sample of oil and we're heating it to 250 degrees Celsius for an hour, trying to burn off any light materials.
250.
Yep.
My God.
Yep. It's just basically a giant vacuum pump, and we're just trying to heat up the oil and pull off any light base oils that are in there.
What's the purpose of that?
So the purpose of this is when you're building or formulating an oil, you want the oil to stay in the engine. If you start to formulate an oil with really thin base stocks and too much viscosity modifier, you can actually start evaporating oil out of your engine. And so this is a test that we use that AMSOIL actually brought over to the United States and was the first to actually do the test
I'll be damned.
and make it a standardized test
Yes.
to make sure that our products through the lifespan of the oil stays in the engine.
Interesting machine. 250 centigrade, did you say?
Yep,
That's up there.
it's up there. So over here we have our 4-ball wear tester that we use for measuring oil's resistance to wear. And as you can see, we've got a lot of dials and gauges here. This one we can use to set our temperature. We usually run between 75 degrees Celsius or up to 150 degrees Celsius. Here we have our pressure settings, so we can set it to any PSI rating we want, low load or high load.
Yep.
And here we have our speed, so we can set it for slow rotation or we can go to high speed rotation.
So there's 3 balls and a 4th
Yes. So we have our,
into the nest of the 3.
yeah, so this the sample goes in this cup here, and then we put ball bearings inside. And there's a 4th one that goes in this chuck. So it's basically like a drill press that it sits like this. And then when you put it in the unit, we pressurize it to our pressure setting, and then we'll run it for an hour.
Got it.
And then we use standardized test
So
bearings.
there's a test ball bearing.
Yeah.
This ASTM standard.
Yes.
Got it.
So over here we have our 4-ball wear scar measure.
All right.
So yeah, we've got a microscope hooked up to a computer. And what it does is once the test is complete, we can actually take photographs of the wear scars and we can measure them. So as you can see here, if we look at 2 products that are run at the same settings, you can see how the size of this wear scar,
Yes.
and then if I pull up this one, you can see how much bigger this wear scar is.
God, yes.
So very quickly you can see that one product is better than the other when it comes to wear performance.
What's the magnification?
We're only going to 4x.
It's just 4x.
Yeah.
This is all ball bearing.
Yep, this is all
This
ball
is
bearing.
just a spot. Mm-hmm. Yeah.
Yeah, we're zoomed way in. This one you could probably see with your naked eye. The first one we looked at, this one you're not going to be able to see that with your
Yes,
naked eye.
yes.
You can only see it with our scope.
So what are the differences in scarring here? What am I looking at?
Well, Gail, we're really looking at boundary lubrication here. So this is a test that simulates the type and the quality of EP additives that we have in the system. So
EP standing for
extreme pressure. Yeah, so we've got some pretty good contact on those ball bearings running over there.
Yes.
And that's creating a wear scar. We talk quite a bit about sacrificial layers of protection.
Yes.
And we're really stressing the chemistry here. So if you don't have the right chemistry in here, you're going to get a wear scar that looks like that versus that much smaller one that we saw before.
Yeah, it's destroyed. It's
This
totaled.
stuff, yeah, and this stuff
Yeah.
happens in a hurry if you don't have the right chemistry in there.
So this is our foam bath. We use this to run industrial products, compressor fluids, motor oils. What it does is we just force air through at a specified flow rate through the oil, and we measure how much foam actually builds up.
At varying oil temperatures.
At varying temperatures. We run at 2 different temperatures. We run at 24C and 94C.
Got it.
So one for cold temperature applications and another one for warmer, more engine-like applications. So what we do is we have these giant grad cylinders in here filled with oil, and then what we'll do is we'll just actually send the compressed air through the oil, and it's like a tiny little fish bubbler on the end of that.
Got it.
And so it actually forces bubbles into the oil, and hopefully we'll see some foam. Yeah, so on the left side we have a competitor product, and on the right-hand side we have one of our compressor oil products. So we're doing a heads-up compressor oil comparison.
This is for air compressors.
This is for air compressors.
Yes,
Air in the oil does not provide good lubrication.
absolutely not.
Yeah, so
Aeration is the enemy of engines.
exactly. So
Yes.
we make sure that any product we formulate is not going to create foam or keep air in the oil. So we have to make sure that we maintain good oil lubrication.
In other words, air is not a good lubricant, just so you know. Very low viscosity.
So how are we doing over here?
Well, you guys are winning grandly.
Yeah,
It's
so you can see
ridiculous.
on the left we've got some, it's almost looking like a beer.
Yeah, that's the nitro right there.
Yeah, got a good head of
Yeah.
foam on that one.
My God. Yeah.
Yeah, so not only do we measure how much foam actually builds up, then we also give it 10 minutes to settle and defoam.
Yes.
Yeah.
So you measure defoaming
As
rate
well,
as well.
yes.
Or recovery. Mm-hmm. Yeah.
A lot of people don't understand the destruction that happens when you get an air bubble going through a confined space in an engine. You know, you think about the extreme pressures that that's under. So you've got air at atmospheric pressure that gets compressed to a very high pressure, and then of course that air bubble carries water also.
Yes.
And so you've got superheated steam right in that very compressed area, and that doesn't do a lot of good things to metal surfaces, you know, as it gets under higher and higher pressure. Well, I think this is going to bubble out the top, Dale.
Okay, good.
Whoa.
We've gotten close a couple times.
Well, you guys, you're winning here. Big time. That is insanely different. My God, and that's an actual commercial product.
Yep. All right, so over here we've got some oxidation going testing on.
What are these machines called?
So we call this a hot oil oxidation test. It's basically a giant oil bath running at elevated temperature, and we're just pumping through. This one's actually running pure oxygen.
All right.
So yeah, we have our own supplied oxygen so we can accelerate the testing. So since we're using straight oxygen, we can pretty much quintuple the amount of testing,
Yes.
accelerating it.
Yes.
And so what we're actually doing, we've got a huge study going here of some different compressor oils that we're working on formulating. And as you can see, some of them, there's no brown staining, so we're looking for varnish buildup.
Yes.
So yeah, so if I can pull this tube out, you can see that the oil's still pretty brown. And there's not really any varnish buildup on the sides of the glass. If I pull the one next to it, you can see there's already staining and varnish building up here
Absolutely. Yes.
in our reflux area. And then if I pull it up, the oil's already black. And you can see all the soot deposits starting to form.
Yes. Huh. My God.
So we can do in 13 days up here what it takes a car to do in 6 months. So we can actually use this. We'll actually blend up different oils and we'll let them run for 13 days, and then we'll actually take the oil out and we'll run testing on it. So we'll measure the viscosity to see what the viscosity increase is. We'll actually measure the foam to make sure that the defoamants are actually doing their job after the oil's been in service.
Yes.
We're also looking for varnish. We're also looking for oxidation, wear. So we can actually use these and put them back into a different battery of tests on the other side of the lab.
What's a normal atmospheric oxygen content?
So 20%. So the Earth.
So this is 5 times.
Yeah. So this runs at about 95% oxygen.
Got it. So that would accelerate the test.
You guys were talking earlier about water and corrosion,
Yes.
rust prevention. So here we actually can run a test in our laboratory with some steel coupons, and as you can see, if you have proper rust corrosion protection, you can actually prevent rust. And over here on a competitor product, they don't have it correctly formulated. So like Dan was saying, you just think that oil by itself
Would protect the
protect the
surface, yes,
surface.
yes.
Yeah, these coupons, we actually dip them in oil and we hang them in a giant cabinet that lives in 100% humidity. So these coupons are just rotating 24 hours a day for weeks on end.
Yes.
And we basically run them till failure.
These two have been in the cabinet?
Yeah, these two have been in the cabinet for over a month.
Same with these.
And same with these, yeah.
These were all coated with a lubricant
Yes,
to start with.
to start with, yeah. And whatever oil stays on them, stays on them. And that's all that's protecting the metal from corroding.
What lubricants were they?
So a lot of these we look at for our power sports applications, where like motorcycles or side-by-sides where they have to be stored all winter long. And so there's a lot of opportunity for moisture to sit on the metal surface for long periods of time
Yes.
in that engine. So we need to be able to protect that engine so that when you take it back out in the summer, you don't have to worry about your engine parts all being corroded.
Do you guys have a hot rod you store during the winter? So this is AMSOIL, and this is somebody else?
Yes.
All right. Brand X.
Yep, Brand X.
All right.
So right next to it, we also do some copper corrosive testing. What this is we basically take these little tiny copper strips and we shine them up. We polish them with emery cloth and some abrasive powder, and we soak them in oil for between 3 to 24 hours.
Yes.
At various temperatures. And as you can see, depending on the level of sulfur content in the oil, it attacks that soft copper. And so you can see here, this one's actually fairly shiny and bright, and this one's already becoming brown and dull.
These are your yellow metals, right,
yes.
Dan?
Yes.
Yep.
There's actually an ASTM method that you match it to. So you basically run it for your amount of time, and then you basically match your coupon to the coupon that looks the most similar. So you can see like that's like a 1A.
Yep.
And then this one's probably somewhere like 3A heading towards a 3B.
Yes, see that.
Gail, this is one that's particularly important for people that are into additives. So some of these additives that are added to oil have high sulfur content or other corrosive materials that are going to attack these bearing materials first. So here's an example of sulfur going after this bearing material, and you can see what the attack looks like initially.
Exactly.
And you can imagine what it would look like if it's under pressure and running continuously, because you just abrade that surface, that stuff comes off, and then you get more sulfur attack, and then the stuff comes off more, and pretty soon you got no bearing material left.
Exactly.
That's how it goes.
The thought goes through my head, how do you know what's in an aftermarket additive package?
Yeah, we often ask that too.
You're buying some aftermarket stuff to put in your oil that might have a negative effect
Yeah.
when you're putting it in for a positive effect. All right, what do we got here?
Okay, Gail, I think you're really going to enjoy this one. This is our cold pour point test that's very visual. So when people want to see, they say, what are the differences in oil at different temperatures?
Yes.
We've actually got oils back here in a freezer down to minus 35, and we bring them out, and then we just show people visually, our stuff pours better at cold temperatures. You don't believe me? Well, here you go.
All right.
So Dale's going to pour it, and we're going to see a difference in a couple different formulations in terms of resistance to fluidity here.
Cold flow. Well, that's definitely different. Look at the viscosity of this.
Yeah, one's coming out kind of like honey, and the other one's flowing pretty decent.
Beautifully. The stuff is 35 below 0 centigrade.
If you can't get oil to where it needs to go, it can't do its job.
Well, I tell you what, I want to cold start with the one on the right. That is incredibly visual. All right, so is there any chance you have any diesel oil we could test?
Dale?
Yeah, we can do that.
All right.
I've got some for you.
You have some Rocky Road in there too? I'm just
No,
a little ice cream
no Rocky
while I'm
Road.
waiting.
All right.
Well, they're different colors, that's for sure.
Yeah.
So what have we got here? The dark one is what, and the light one is what?
So we've got some Dello diesel oil, 15W40.
All right.
And we've got AMSOIL diesel engine oil, 15W40.
All right. 35 minus
35 below.
35.
So let's go.
Yeah, let's do it.
Whoa.
Oh my!
You saved the
God.
best for last.
Jeez.
Holy cats.
Oh, you kidding
All
me?
right.
You are kidding me.
And we see 35 below.
Yes.
Maybe you got to go to the mountains in California. but
We do,
see it regularly.
We do cold start for our JLTV engines, military engines, at 40 below. No wonder it's so hard to crank.
For a 1540, it's tougher to formulate for cold temperature properties.
And I think we're
'cause of
running
40 weight.
something like a 1540. Come to think of it. Wow.
Yeah, that's a big difference, Dale.
Oh my God.
Thank you. We saw how oils are formulated
Yes.
up here. We
Yes.
saw how they're tested. That's not where it ends for AMSOIL. Maybe
Yeah.
for other companies it ends there. We go down to our mechanical lab,
Okay.
and we're actually taking these lubricants and putting them in actual equipment. And that's what we're going to see next.
And I think that equipment might be a small block Chevy.